Welcome back to the engine history. Many of you who work in the trade have probably asked this question. How can an alloy cast engine from the 1950s still operate reliably under extreme load in thin, high-altitude air? Listen closely to the whistle of this intake stream. This is the cutting sound of airflow being forced into 27 liters of combustion capacity on the Rolls-Royce Merlin 38 V12 power plant. More than 60 years have passed since Lancaster bomber squadrons were retired, but if you prime the ignition timing correctly, this heavy mechanical block fires instantly with a crisp, aggressive crackle. The core reason this iron can produce up to 1,400 horsepower is its two-stage boost system. This mechanical supercharger compresses the intake charge and holds manifold pressure steady. It keeps the Merlin from ever running out of breath or dropping boost as it climbs to extreme altitude. Let's cut deeper into Merlin's configuration. Using a V12 layout with a closed-loop liquid cooling system, this engine proves the near absolute machining tolerances of the metallurgical engineers of that era. Every oil line, every crankshaft bearing saddle, every connecting rod support is built thick to withstand massive torsional stress when engine speed is forced up toward 3,000 revolutions per minute. That violent pull reshaped post-war aerodynamic design thinking, and it locked in Rolls-Royce's reputation for hard-hitting manufacturing quality. If the Merlin is the benchmark for a V12 layout, the Bristol Hercules Mark III power plant is the peak of heavy-duty radial engine design. At the West Green Pocklington Airfield test site, the sharp, clipped firing tone of the Halifax era comes back to life after more than half a century in storage. The money feature of the Hercules is that it completely eliminates the traditional poppet valve and spring system. Instead, it uses a fixed sleeve valve mechanism. This sliding sleeve design increases intake and exhaust port area and reduces friction losses in the valve train. That is how it maintains remarkable mechanical durability during long, high-demand sorties over German airspace. Before we go deeper into the priming and ignition procedure for a radial power plant on the M2 tank and examine the compression ratio figures of the 1912 Gardner stationary engine, if you love mechanical specifications, live for the smell of oil and grease, and crave the vibration of big pistons, subscribe to the Engine History. Don't forget to turn on notifications so you can follow these teardown and measurement sessions when century-old steel blocks are cleaned and fired again. Your support is practical funding that helps the team keep disassembling and documenting these historical engine specifications. Still inside the radial ecosystem, the Continental W679A is one of the most versatile work engines of the 1930s. With a 7-cylinder, forced, air-cooled layout, it throws away the complex radiator cooling system completely. By removing the risk of coolant leaks and burst hoses, it stays stubbornly reliable across battlefields. From the nose bay of the Stearman PT-17 trainer to the engine compartment of the armored M2 light tank, the entire power plant weighs just over 200 kilograms. Yet it delivers an excellent power-to-weight ratio that carries the Allied high-intensity pilot training program under continuous high RPM use. Looking back into Merlin records, the restoration shop is currently holding an original Merlin 25 from the John Smith collection in New Zealand. Any working mechanic would stare at the service history and flinch. After all these decades, this V12 shows only 84.3 hours on the hour meter for run-up and load operation. Valve clearances, piston rings, and crankshaft bearings still sit almost exactly at their original 1940s factory tolerances, with boost pressure tuned specifically for the wooden airframe de Havilland Mosquito. The Merlin 25 pushed that aircraft into true high-speed performance. Covering long-range reconnaissance missions with sustained revolutions per minute for hours at a time. Watching the camshaft system and the supercharger drive run smoothly on the Omaka test stand, anyone in the trade can judge the alloy quality and the machining skill of wartime Britain. Every intake, fire, and exhaust cycle hammering the crankshaft is a hard statement. A statement about manufacturing capability, impact resistance, and material load limits calculated in extreme detail by Rolls-Royce engineers in the harshest years of the war. Step back to the era before boost systems and direct injection became common, and mechanical power relied on minimalist designs like the 1912 Gardner 2F stationary engine. Fired on gasoline or kerosene, this twin-cylinder engine breathes naturally and uses a hot bulb ignition system. The operator does not use an electric starter motor. They use a blowtorch to heat a cast iron hot bulb until it glows, then hand-turn the flywheel to build compression. This priming ritual demands absolute precision in crank angle and hand rhythm. The structure is crude, but it delivers brutally stubborn low RPM pulling force for early 20th century marine propeller shafts and industrial line shafts. To close the list, the Ford V8 flathead was the design that brought the V8 layout into mass production. Using a simple side valve arrangement, an easy-to-cast iron block, and minimal moving parts, it was produced in more than 15 million units. The fatal weakness of the flathead is airflow. The intake path is forced to turn sharply, limiting breathing and keeping RPM from rising very high. Even so, thick block walls and the ability to modify the oiling system, camshaft, and carburation turned it into a legendary mechanical platform for fabricators and the high-speed hot rod scene. Whether it is the supercharged intake whistle of the Merlin 38 carrying a Lancaster, or the slow, clipped exhaust beat of the Gardner 2F down in a ship's engine room, every one of these mechanical designs proves the same thing: absolute toughness under load. These iron and steel power plants were built to work hard and be pushed to the limit of their output. Thank you for watching the engine history break down the specifications today. From a working mechanic's point of view, do you rate the load-bearing structure of the Merlin V12 higher? Or do you prefer the practical, easy-to-modify, side valve design of the Ford V8 flathead? Leave your analysis in the comments so the crew can compare notes together. Wishing you strong health, and see you again in the next technical teardown session.